Hello, everyone. Welcome to this webinar, Aquila in Action, Optimization, Machine Learning, and Simulation with QuEra. My name is Yuval Boger. I'm Chief Commercial Officer at QuEra, and I have three of our distinguished scientists with me, Milan, Kornjaca, Fangli Liu, and Jonathan Wurtz. Hey, guys. And today we're going to focus on Aquila, our 256 qubit computer. So we covered the host. I just do sales and marketing, but these guys are the real deal. And we'll have 5 parts to this webinar. I'll give a short introduction to QuEra and Aquila. We'll talk about machine learning with Aquila. That will be covered by Milan. Simulation with Aquila by Fangli. Optimization with Aquila, Jonathan. And then we're going to leave time for question and answers. There is a Q&A box on your screen. Feel free to submit questions at any time. We're going to monitor them and try to answer as many as we can. You don't have to wait till the end. You can submit whatever you want. So first about QuEra. QuEra is headquartered in Boston, close to Harvard and MIT. That closeness is not just a geographical closeness, but also a sort of a scientific closeness. A lot of the work that we do was started at Harvard and MIT. We still collaborate with them very deeply. We publish together. And so it's really a wonderful relationship. We build computers using neutral atoms. There are many ways to build quantum computers, superconducting, photonics, trapped ions, and so on and so on. We believe that neutral atoms is really the best way to reach where we all want to go, fault-tolerant, large-scale quantum computers. This is for a number of reasons. Scalability, we can have many, many qubits on a single machine without needing to network, room temperature operation, the connectivity between the qubits, that we have all-to-all connectivity, and many other things that make neutral atoms very unique. And we believe that of the neutral atom companies, we are clearly both the scientific leader as well as the commercial leader in terms of our deployments of machines, success in sales, and so on and so on. We're going to talk about Aquila. Aquila is our first machine that has been available on the cloud, on the Amazon Braket Cloud since November of 22. And today, we'll talk about both simulation, machine learning, and optimization using Aquila. How do you work with QuEra in general before we get into the beef of the webinar? You can work with us in 3 ways. By the way, we're hiring lots and lots of open jobs on our careers page. But we sell machines. We sold a computer to the AIST, the National Institute of Standards in Japan. We also have a deal to deliver a machine to the UK National Program, and we're negotiating additional deals. So we're happy to provide computers on premises, usually in conjunction with HPC centers. You can access our machine via the cloud in many ways. And we also do joint development. We believe that quantum computers at this early stage require really full stack integration between hardware and software. And our algorithms team is eager to work with you to make sure that you can get the best implementation of the problem that you have to work on our computers. Aquila itself, as I mentioned, was launched in November 2022. We're a couple weeks away from its 2nd birthday. We'll have a big celebration at QuEra, just like we had for the first one. And what's amazing about this machine, first, it's a 256 qubit machine. The other thing that over these 2 years, we've seen so much work done, many countries, many organizations, many users, numerous publications. So it's been very useful in advancing the science of quantum computing, as well as machine learning, optimization, and simulation. The other thing that's amazing about Aquila is that it's still, even 2 years later, is the only publicly accessible neutral atom computer in the world. And that is one reason that we, as I mentioned earlier, we believe they were both the scientific and commercial leader in neutral atom quantum computing. What problems can we solve? machine learning, both classification, prediction. We'll talk about quantum reservoir computing, many different sets of optimization problems, simulation. So this is exactly what we're going to cover in this webinar. I want to give you a peek inside the machine just to really quickly explain how the machine works. In neutral atoms, individual atoms, in our case, rubidium-87 atoms, are the qubits. The way we work on Aquila is we take these atoms, we arrange them almost in arbitrary positions wherever we want, and then we excite them in a sort of time-dependent Hamiltonian and then measure the results. And so what you see in this image, let me click on it so you'll see the video. You see sort of the three stages of this. On the left side, what you see is that we sort of load a whole bunch of atoms into our vacuum chamber. In the middle image, what you can see is that we're basically arranging these atoms in a configuration that we want. In this particular case, it's a very simple test case where we have a 4x5 matrix. Each of these dots is a single atom. So this is a very small space that's being enlarged on the screen. Then we run the time-dependent Hamiltonian, and then what you see on the right is really the results. And the reason you can see every result is different because of the quantum effects. We basically measure the atoms, measure the qubits that causes them to collapse either to a 0 or a 1 state, and then we perform the measurement. And maybe we start with the first presentation and talk about, if we go back to the agenda, talk about machine learning. So Milan, please go ahead.
Thank you all for the wonderful introduction. Yeah, so let me take over with our work on what we would say is the largest quantum machine learning performed to date on a quantum computer. And this was done on our Aquila. And if you want more details about our work and quantum machine learning in general, you can take a look at our archive that is here below with the QR code. So why quantum machine learning in the first place? Well, classical machine learning, I think hardly needs any introduction to general audience. It is truly become a transformative technology. And if we ask ourselves what led to this amazing success of machine learning and AI, well, we can't forget that all of its success essentially comes from data. And it differs from your usual programming paradigm in the way that you use the data and leverage it. So it is probably, given the huge success of AI and machine learning, it's not a surprise that if we really want to have a robust quantum field, quantum machine learning will be critical for its future. And where would we see the prospect for advantage in quantum machine learning itself? Well, it's again, as with classical machine learning, going back to data. And specifically, we now believe, based on many works, that there are certain types of data that would be advantageous to process with a quantum processor. In particular, if you look at the table here, we are pretty sure that if you have quantum data and we have rising amounts of quantum data from all of the quantum hardware that's out there and in other places, that the quantum computer would be uniquely positioned to essentially perform quantum machine learning tasks on it. But what we also saw more and more is that classical data can have certain quantum correlations that can sort of also put it into the same category. So the prospect for advantage is there. It's in all kinds of both quantum and let's call it hidden quantum data that we have. However, how do we deal with this data? What are our current quantum machine learning algorithms? Well, it turns out that the currently dominant algorithm is something called variational quantum machine learning. It's essentially a quantum version of a neural network in which you replace so-called hidden nodes of a neural network by parameterized quantum gates. And then your whole goal is to feed the data and in the training process, optimize parameters of these gates in order to get a good performing model out of your quantum circuit. However, it turns out that there are some fundamental issues with this sort of fairly ubiquitous algorithms in literature, and they're mostly related to the sort of the cost of performing the optimization over the parameter space, which requires multiple queries of quantum computer and going through sort of classical quantum hybrid optimization loop. And even more fundamentally, it turns out that sort of the parameter landscape of these algorithms can be very problematic. It can have sort of so-called barren plateaus, which means they will be hard to train, or it can even be corrupted by noise and so on. So with all of this, it's probably not a surprise that current experiments with variational quantum algorithms and quantum machine learning in general are very often rare, small, and with limited quantum advantage potential. And we really wanted to tackle all of these points. And the algorithm that we choose to do this on our Aquila neutral atom system is the reservoir computing algorithm. And here is the basic overview of quantum reservoir computing with neutral atoms. The algorithm, of course, starts from the data, and it includes arbitrary, sort of optional pre-processing step on the data, which just brings it into the form that can sort of fit the quantum computer and be suitable for encoding. And the next step is critical. It leverages all the degrees of programmability in our Aquila system effectively, and it's the encoding of the data into the system itself. It can be done through the time profile of the pulses that we do on the atoms. It can be alternatively done through the programmable positions of the atoms or programmable spatial pattern of the pulses, such as this local the tuning pulse shown here. Whichever way we encode the data, the next step is the same, and it's the critical step of performing quantum dynamics on large neutral atom arrays. We then probe that dynamics several times during its evolution, collect the observables from that dynamics, and pass it to a simple classical post-processing method. It can typically be something like a support vector machine or linear regressor, which really doesn't require any training, and in particular, it doesn't require training of quantum parameters. Once we have our model trained, we can sort of repeat the same process and infer on the test set. And immediately from sort of the setup, you can see several important advantages. I won't go over all of them, but some critical ones is that the problem of trainability and resource use that variational algorithms had is solved by not having sort of to train the quantum part repeatedly. The great thing is that it's a general purpose algorithm, so it can really tackle all kinds of data, as I'll show. And they also show some of the consequences of it being very scalable and potentially classically intractable. So without further ado, let's go into some of the results. Again, our paper here in the corner shows more. So this is a basic sort of proof of concept of the algorithm on our Aquila quantum computer, and it's on a binary data set made out of MNIST data, which is essentially a task of recognizing digits 3 and 8. And here is the performance of Aquila versus several classical methods. As you can see, our QRC method in sort of ideal simulation reaches the performance of the classical methods on the data set, and once we run it on Aquila, we can see that our experimental results in orange is with 0.5% of the simulation taken with the same number of experimental samples. And furthermore, this is how our test accuracy scale is the number of samples. In practice, the number of samples that you draw on machine is one very important factor in determining the performance of the QRC. And here as a function, number of samples are results on Aquila sort of behaves very similar to the simulation result, and it consistently grows in performance. We didn't only tackle sort of this image classification tasks, such as in MNIST. We really tried to expand across data sets. And here is an example of our quantum reservoir computing tackling a time series prediction data set. This is a sort of a simple time series task, but very often used in literature. and it corresponds to predicting the intensity of a laser in a chaotic regime. It's a univariate time series here, and you can see some of its features on the left. And then here is a simple example. How do we encode these features in our machine? In this case, we're showing encoding into the profile of the global detuning pulse. And then very interestingly on the right is sort of an insider look, if you'd like, into the outputs of the quantum machine on this data set. On the top is the simulation, on the bottom is experiment. And yeah, if you look at sort of these, we call them embeddings, you can see how sort of the features that we see in the embeddings sort of match the original data set and sort of repeatedly express it in different ways. And furthermore, if you compare simulation and experiment, you can see that in both of these, we can see sort of the characteristics of the original data very clearly, and both of them match each other very nicely, with one additional caveat, and that is experiment has this sort of noisy appearance, and that is because of the finite number of shots that we take for generating these embeddings. And if you look at this great agreement between simulation and experiment and embedding, it's probably not a surprise that when you actually look at the performance of the test set, Aquila is performing as well as a cohort with sample simulation, and both of them capture the test sets fairly well. And furthermore, something that's of significant practical importance is that on this data set, we tried all of our 3 encoding methods. And as you can see in simulation, we sort of have predictions of how would their performance be expected to behave. And in particular, we predicted local and position encoding, so encoding into the positions of the atoms, and the local detuning, which is a new experimental feature of Aquila, should be the best. And indeed, this is what we also saw on the machine itself, with an additional caveat that the local detuning is sort of suffering the least, pretty much almost no performance degradation over the perfect simulation. So that's pretty much the encoding that we sort of suggest you to run if you want to try the QuEra's yourself. So these were sort of experiments that were aimed to prove the concept of the QRC and sort of test different encodings. But now we really wanted to scale up our experiments. And the data set that we took for that is this data set of healthy and diseased tomato leaves, with the goal of course, classifying which one is as healthy and which one has which disease. And we encoded it very simply by just downscaling the images and encoding them into the positions of a large 2D Rydberg arrays. And this is how our results look as we scale up our system size, or according to the number of pixels that we encode, all the way from 9 to 108 qubits. On the y-axis is the test accuracy on the dataset, and the x-axis is the number of qubits. And you can see that we have consistently increasing performance with the number of qubits. And furthermore, as we increase the performance, we are getting very close to sort of what classical methods achieve at best on this data set. And it happens so that at 108 qubits, which is the largest experiment that we run, we also achieved the largest successful quantum machine learning reported in literature today. And as a comparison, the previous record was from Google with 40 qubits. So this is really sort of scaling up quantum machine learning significantly. However, we didn't only want to just scale it up and leave it at there. We also wanted to say, at these scales, we should really have trouble sort of getting these quantum embeddings classically. And we wanted to ask, is there a potential for quantum advantage in this potential interactability of embeddings? And for this, we took a recent idea of sort of kernel-like relabeling, a construction that sort of takes 2 kernels. It can be 2 classical kernels. It can be quantum and classical kernels, and sort of uses the difference in their geometry to reconstruct a dataset labels such that there fits sort of this difference in the geometry. So as a result, if you take your dataset, you are left with the classical dataset with the same features as the original, but with labels permuted according to the kernel geometry. And once we do this sort of synthetic data set construction, if you like, on Aquila, we observe comparative quantum kernel advantage. This Aquila that was previously slightly worse than classical kernel, mainly due to finite amount of samples that we draw on hardware, is now has 7% accuracy benefit over the classical method. And furthermore, if we look at the skewing with the number of shots, this accuracy benefit is consistently seen, and it sort of matches what is expected from exact classical, exact numerical simulations of Aquila, which is just showing that this is truly a quantum effect. So in conclusion, we look into a novel quantum reservoir learning algorithm with neutral atoms. We were able to do quantum machine learning on unprecedented scale compared to what was done before, and we show some quantum advantage potential. However, if we really want to sort of discover where this can lead us, we need to look at the data. We need to find the data where quantum machine learning really has benefits. And for this, we would really like to work together to find these use cases. Again, if you'd like, here is our paper. And here are the tutorials in both in Julia and Python that cover some of the basics of the algorithm.
Thank you, Milan. There was a question from the audience whether the classification work that we've done only works on images, or can we take non-image data and perform the same type of workflow?
Yeah, that's a great question. Absolutely, you can take sort of whatever typical classical data set and try to run into our pipeline. You will be able to do this because in the end, sort of we record numerical values of our feature vectors into the machine. In this case, it might be the value of a pixel, but in your case, it might be some other numerical features. So absolutely, it's very flexible in terms of data set that you can encode.
Excellent. And is there a good way to know if a data set is suitable for quantum reservoir computing, whether using the simulator or in some other method?
Yeah, that's I would say the big question here. And unfortunately, for a general data set, we don't know. And the best thing we can do is really try, which I highly encourage doing. In some cases, for example, if you know that your data set is generated on a quantum computer, so for example, if it's some kind of quantum simulation data set, we can have a very good guess that it might be suitable for reservoir. Or if you believe your data set might have something quantum in it for other reasons. But otherwise, unfortunately, you just have to try, because the construction tells us that there exists such data sets, but we don't know what they are.
Excellent. Thank you very much, Milan. We'll leave room for additional questions at the end. But for now, Fangli, if you are able to start your part on simulation, that would be wonderful.
Sure. Let me share. Yeah, thanks to you all, and thanks Milan for the wonderful presentation. So today I'm going to tell you about some of the recent updates on quantum simulation with our quantum computer Aquila, analog quantum computer. So let's see. So as you already hear from the previous talks, different from the gate-based quantum computer, our system is described by quantum many-body Hamiltonian, where the basic elements has mainly three components, where you can have the interactions between the qubits, and or you can have this local detuning field, and also the Rabi drive, which can couple the ground states and the Rydberg states. And there is a lot of flexibility in this Hamiltonian that the user can tune. Firstly, you can place the atom in different locations so that you can engineer different form of the interactions, so that you can also do some geometry-based quantum simulation. And also you can tune the waveforms into pretty much arbitrary forms, of course subject to some constraint. For example, here you can make them at like the gate-like pulse, or you can do some very slowly change of the waveforms so that you can do annealing, or you can pretty much engineer different arbitrary shape of the waveforms and treat them as variational parameters to prepare your states to achieve higher fidelity. So before I go to some of this detailed work that we have been doing, I would like to share some of the partnerships that we have been doing around the direction of the quantum simulation in the past few years. The first one is the partnership with NERSC. NERSC stands for National Energy Research Scientific Computing, which is a research center under the Lawrence Berkeley National Lab. And in NERSC, they have very high performance computing devices called a perimeter. And so in this collaboration, we're trying to, we started early last year, we're trying to work very closely on the quantum simulation project that are relevant to the DOE mission. And what we're doing is that we're trying to finding some problems and then trying to use both the classic HPC and then also use the QuEra QPU, trying to benchmark and also compare the performance of the quantum and classic hardware. And besides the scientific research, we also trying to enlarge the engagement from the broader community, trying to help education of the people to use Aquila. For example, recently, NERSC opened a program called QCAN, so that we're seeking proposals from the community so that they can submit the proposal. For the selected winners, we're providing the machine time of Aquila and also providing some of this scientific advising for them to make sure their project is successful. So here I would like to give you some overview of the scientific outcomes from the first year engagement with NERSC. So in the first, as I mentioned before, what we are trying to do is trying to use Aquila to study some problems that are relevant to the DOE mission. In particular, in this project, we are trying to using the available capabilities of Aquila, trying to study some very interesting physics phenomenon called bubble nucleation or confinement physics. So these are very relevant to the high energy physics and also the early stage of the how the universe begins and how it evolves. And we're very lucky to find that using the interactions available in Aquila, we are able to engineer exactly the same phenomena and give us some further insights how we can understand the confinement dynamics in the non-equilibrium way and also the bubble nucleation dynamics. And we're able to publish the paper earlier in this year, post on arXiv, and both of them are published in PRB recently. And besides this, we're also trying to leverage Aquila to engineer more interesting quantum states, either by place atoms into very non-trivial geometries, or trying to use the waveforms to engineer non-trivial, very entangled quantum states. And we have a paper also on arXiv, and you can see that we use Aquila to engineer these systems, and we submitted this paper several weeks ago to IEEE Quantum Week, and we're very happy to see that this was selected as the best paper award in this conference. And and currently we are in the second year engagement. There are still a lot of very interesting work and scientific work going on in the quantum simulation, including like the quantum phase of matter and also quantum dynamics and also quantum and also chemical mechanism, etc. So besides the NERSC, another partnership I'd like to share is with the Purdue University and QSC, which is also, QSC stands for the Quantum Science Center, is also a quantum institute under the DOE. So in this partnership, again, we're trying to finding problems and study problems that are interested to the DOE. And this collaboration has been a few years also, has been started by working with the Purdue or folks to develop the theoretic idea. And we have been pretty much have very good understanding of the theoretic idea. And earlier this year, Amazon provide us the credits so that the Purdue side, they can run this quantum simulation and obtain the experimental results. So this is a slight different from the academic lab, where you need to direct engagement with the people who run the experiment. Here, you can just submit your job from the cloud service and get almost exactly the same results as compared to the lab. And just a very quick overview of the scientific project that we're doing. So in particular for this project, we are putting the Rydberg atoms into the Shattuck-Sutherland lattice model. As we mentioned before, we can pretty much engineer very different geometries. And this is quite interesting geometry because it's relevant to a lot of real materials, especially the so-called rare earth tetraborate family materials. And there has been a lot of classical studies trying to understand the phase diagram of these materials. As you can see, there are different phase regions. And so in this study, what we are doing is, as we know, Aquila is able to have some quantum effect by adding the Rabi oscillation into the system. And this is also relevant to the real material if we shine some magnetic field trying to excite the system. So this is a real quantum simulation trying to understand some real material instead of trying to simulate some theoretical models. And adding these quantum terms in the quantum phase diagram, we immediately see there are very interesting phenomena. First of all, we are able to induce a new order phase that is 2/5 or 4/5 order phase. The second phase that is by quantum is that we are able to see a novel, very internal quantum phase called quantum dimer phase in the quantum region. And from the experiment, we get almost exactly perfect agreement with the quantum phase diagram, and we're going to submit the paper later in this year. And besides the involvement, we also support purely academic collaboration from the universities. The first example is that we work very closely with Professor Yannick from Iowa University. So in this project, we're trying to put the Rydberg atoms into 2-leg ladder up to 92 atomic qubits. And what is interesting is that we found that in this phase diagram, there is a region called the floating phase. And this floating phase has been proposed like several decades ago. This is the first time we use the quantum system to really try to prepare the states and get very clear signature of the floating phase. And besides this, we also collaborate with some thought leaders in this field, including Professor Peter Zora's group. So in this project, we're using Aquila to implement the model that is relevant to lattice gauge theory. So in particular, we're trying to understand in which parameter region in our quantum simulation we can simulate either the stream breaking or the stream non-breaking phases, and we're able to see it from the quantum dynamics of our system. So as I already mentioned a few examples of the collaboration, now I would like to just quickly go through summarize the major two types of problems that Aquila is good at for quantum simulation. So the first one is preparing the quantum states, quantum ground states. And so the idea is that if you have some geometry and you, due to the interactions and also the quantum effect, you can get some of the phase diagrams. And then we can, using the adiabatic process by leveraging the flexibilities to tune the omega and also the T-tuning, so that we can go from the very simple states to the very non-trivial quantum order states. And as you can see here, we can go all the way to the all the zero states to the non-trivial Z2, Z3, and Z4 states. So here I'm showing you an example of the very simple one-dimensional Chim's case, where we can prepare the target states is the so-called Z2 states. That is, we have Rydberg excitations in every other qubits. And after the adiabatic process, as you can see, we indeed get a very high probability of these states. And this can also see clear from the correlation functions of the two different sites of Rydberg density. So the second class of the Rydberg atom project that can be do is for the quantum dynamics. For the quantum dynamics, that we can study the so-called, give you example, is the so-called quantum scars. So the quantum scar was first found very early in the quantum Rydberg paper. That almost the very first paper of the paper talking about Rydberg atom wreaths. And it was later people found that this phenomenon is related to very non-trivial structure in the Hilbert space, and this is then called as the quantum many-body scars. And so in the experiment, what we do is we first trying to prepare the Z2 states, and then we see that after we tune this detuning field, the system can oscillate in between the two different order states, and this oscillation can keep for a very long time. And indeed, we can see this from the experiment very, very clearly. Here, we're trying to prepare the states. As you can see, this states has a very high fidelity. Also can be seen from the probability of the neo states. And after this quench, we see this two order states has been going back and forth for very, very long oscillation period. So finally, I would like to mention a few new features that has been added to Aquila recently. The first one this is already public accessible from the AWS. So the first capability is the local detuning. So instead of adding the global detuning that has a uniform field on each of the qubits, now we can control each of the individual qubits to some degree of freedom. So this will allow the users to have more programmability to the qubits of the states or trying to prepare initial states. So the second flexibility is that we allow we relax some of the constraints in the qubit arrangement. Previously, the users are restricted to make sure the atoms, the raw spacing is bigger than 4 micrometers. Now this constraint goes down to 2 micrometers. And previously, the field of view height is 75 micrometers. Now it's going to be 100 micrometers, so that you can place more qubits in the system. And this will open up a lot of new opportunities in the direction of analog quantum simulation, including we can program disorders, we can try different initial states, prepare them, and also we can study non-trivial quantum dynamics, and also we can engineer different exotic analysis and also study one-dimensional and quasi-1D systems. So finally, I would like to mention some outlook in the direction of the digital quantum simulation. As you know, we are also building a new generation of the digital gate-based quantum computer, and using the gate-based quantum computer, we are able to do many different problems that are relevant to materials chemistry and condensed matter systems, and we don't need to restrict to the particular Hamiltonian forms that I was showing you. And also because our system can be easily scaled into a large scale, and also can move the qubits during the calculation, we are able to do a lot of very interesting problems called long-range by engineer the long-range connectivity, or by scale the atoms into several hundred, even thousands of the qubits. And finally, we're also working on early fault-tolerant digital quantum simulation algorithms, trying to understand whether in the near future we can get some quantum advantage using the digital-based quantum computation. So that's all my talk. Thanks for your attention.
Thank you very much, Fangli. I think one thing that's important to mention is that there are various degrees of engagement with QuEra in these works. So some works, like I think the NERSC efforts that you mentioned, a very deep interaction between QuEra and the user. In some times, we just provide sort of high-level advice and available when there are questions. And more recently, we've seen papers that we didn't know that people were working on it. And we found out about the work just when they published. So it was really completely disconnected from QuEra in terms of support. So whatever works for you as you work for your simulation optimization or machine learning, we're happy to engage as deeply or as slightly as you want. So thank you very much, Fangli. And with that, Jonathan, maybe we could move to optimization, please.
Yes. All right. Let me share my screen. Hide my screen. Good. All right. So in the previous two sections, we were talking about machine learning and simulation. So now in this third section, we will talk a bit more on using our neutral atom hardware for quantum optimization. Now this is mostly based around this recent arXiv paper, which came out a few months ago and is about to be published in IEEE QCE. So the way we do optimization is with our, as Fangli showed last time, our neutral atom cloud accessible computer Aquila, which unlike the other paradigm of gate-based mode, instead does time-dependent Hamiltonian dynamics, which is basically you have some Hamiltonian given here by this Rydberg atom Hamiltonian. And then unlike a set of discrete gates that does some execution, instead you start with some initial state and do some sort of everybody gate to do some interesting and non-trivial dynamics. And in this way, what you're able to do is encode, for example, encode problems through, say, the time dynamics, or the time dependence of this Hamiltonian, or also the position of the atoms in your 2D array. And we have plenty of examples. I believe there's the Aquila white paper linked in the chat right now, which is a great introduction to using this device. Now, what I'm going to talk about today is more about optimization. And I think here at QuEra, we like to take a very pragmatic and practical approach to using our quantum devices, not necessarily for demonstrations, but actually trying to extract some sort of value out of these devices. Now, typically for optimization problems, we have some sort of problem, say things from logistics and scheduling, portfolios to networks. And typically how the standard flow goes is we go from this problem, we encode into some Kubo problem or higher order problem or so on and so forth. Then we, put this onto our quantum device. We do some dynamics, measure some bit string, right? And then from this bit string, this generates some solution. Of course, the challenge is that not every problem necessarily fits into, not necessarily has a good encoding into Kubo problems. And furthermore, not necessarily every Kubo problem or every encoding is a natural fit for quantum hardware. So that being said, there are certain kinds of problems which do have a natural fit onto our neutral atom hardware. The main one is this one called maximum independent set, for which we have an example over here, where basically we have some graph of nodes and edges, and the maximum independent set is the largest subset of nodes such that no two nodes are adjacent. And this problem ends up being very natural for a specific subset of problems from things like antenna placement, networks, power grids, and so on and so forth. If you're curious to learn more, there's this paper up here which details some implementations of maximum independent set. And this is a very natural problem for us, and we've had great success in optimizing this problem because this is naturally the solution to the maximum independent set is naturally encoded into the ground state of the Rydberg Hamiltonian. So for beyond these sort of King's graph unit disk graphs, we can also consider more specific customer problems. So for example, we did one problem with a customer on satellite scheduling, where suppose you want, in an abstract way, we have some satellite flying over the Earth, and we want to take pictures of ground targets, each in a color here, and we now want to basically figure out which picture to take of which target at which time under constraints that the satellite can't slew from one location to the other efficiently. And what we can do for example, is we can say nudge those atoms, nudge those vertices into locations such that it becomes very close to a unit disk independent set, which can then be naturally encoded onto our hardware. However, the challenge is that not every problem is a maximum independent set. So really what I'm going to be asking about here are what are problems and paradigms which go beyond simply finding ground states of Rydberg atoms. And in this way, this actually gets us much closer to our first talk about quantum machine learning, where we're not necessarily just computing ground states, but instead we are using the coherent non-equilibrium dynamics of our hardware in order to execute as a resource to solve problems with both quantum and classical resources. And with this, I would like to introduce this recent paper over here on non-native hybrid algorithms. And the key here is to consider your quantum computer as simply a coprocessor in a larger in a larger workflow. And most importantly, your measurement outcomes are no longer directly linked to problem solutions. And in this way, your quantum resources are acting as a coprocessor so that your measurement outcomes, or your bit strings here, are instead something you can use to, for example, infer structure about your problem, so that you can use sort of these measurement outcomes as say, a quantum hint for your classical optimizer to solve large problems. And the key here is that because we have broken out the requirement that, say, every variable be encoded in a single qubit, this lets you encode large, complicated, and multi-objective problems into relatively small devices, including these analog neutral atom devices. Now, I would like to introduce sort of a taxonomy of these types of non-native hybrid algorithms, of which we introduce 3 in this paper. The first is maybe the most natural, which is a post-processing algorithm, which is to say you have some single bit string and you feed this into some function, which is then, which warm starts like an approximate solution from your bit string to your solution. An example of this would be max cut, which of course we cannot do on our analog mode hardware, but nonetheless is a good prototype example, where here we can take some bit string as some approximate solution, do some greedy post-processing on that to get some locally optimal solution. And we can see that the combination of these two, right, where here this is quantum only, the black line is classical only, and the purple line is this hybrid method. We can see that together these methods can actually do better than one can than they each can on their own. As an example of this, we did a project with a customer on EV charger placement, where we can use this post-processing algorithm, where suppose we have a set of locations on a map where we want to pick locations for these chargers, and this is almost but not quite a maximum independent set. So what we can do is we can still encode this problem into neutral atoms, right? By basically encoding the problem into positions, where this is now a picture of each atom in the device. And we can see that the hybrid algorithm does better, larger value, does better than the equivalent classical only solver to solve this problem, which is a demonstration of a sort of comparative advantage versus the classical only solver. A second kind of algorithm is described as a quantum hit, which, just like your quantum machine learning algorithm, uses expectation values to infer structure about your problem. So for example, here you might use the connected correlation function or expectation values to feed into some function, which then generates some solution. An example of this would be max k-cut on unit disk graphs, which is a nice example because it very much is not encoded into the 2-level qubit. Because here, say you have 3 different colors, which would be naturally encoded in a Q trig. So instead, what we can do is we can use our device to do non-equilibrium dynamics to infer structure by looking at the connected correlation function of nonlinear dynamics, of non-equilibrium dynamics, and then from there we can implement some relatively simple classical spectral clustering algorithms to generate solutions, which can then be, again, post-processed. And then there we can actually see that in comparison to the classical only solver, we also get better solutions than we would otherwise get with an equivalent classical only solver, which is, again, this demonstration of a comparative advantage. The third type is a little bit more complicated, which would be a reservoir algorithm which directly uses the distribution of bit string Z. And for this, we have an example on maximum independent set, but instead of just finding ground states, instead we find an ensemble of low energy states, and then we do a parallel tempering simulated annealing, where we basically use our samples from the hardware as a resource for a MCMC update step. And we can actually see that given particular variational parameters, the hybrid solution actually converges to the maximum independent set faster than the classical only solution. Again, an indicator of this comparative advantage. Good. So this is these non-native hybrid algorithms. We also have another recent paper on generative optimization, which you can see up here, which has a slightly different flavor to it and is much closer to machine learning, which links both optimization and machine learning. And the goal here is to sample from a Boltzmann distribution over designs. And of course, if you take the temperature to 0, then you found the optimal solution. And this ends up combining 2 interesting things. The first is this quantum-enhanced Markov chain Monte Carlo which is a paper from 2023, which proposes to use a quantum device to propose an MCMC update step. Then what we do is we combine this with variational autoencoders, where the latent space is instead replaced with our quantum hardware, where now the latent space is basically the space of bit strings, and the updates are the updates as generated by this MCMC. We're able to demonstrate this for a particular example of metasurface design for optical lenses. And hang on, let me bounce that back. And basically, what we can do is we can see that as basically our latent space is changing, so too does the various designs that we might find as we slowly sample from our Boltzmann distribution. And while we use this for metasurface design, we could also imagine doing this for many other things, from drug design to logistics to engineering, and all sorts of other things. For more details, I would invite you to read this paper up here. But the key here is that we're basically able to use our quantum device to hopefully sample from this Boltzmann distribution faster than what you could otherwise from a classical only architecture. Good. So with that, I would like to conclude with sort of an outlook on optimization with QuEra. So our sort of put two challenges. First is designing performant and scalable algorithms that actually fit to interesting problems. And then the second is, once you have these algorithms, making those hardware specific in a way that you're able to maximally leverage and exploit the particular strengths and mitigate the particular weaknesses of different hardware, including neutral atoms. And to this regard, what we've presented here are these cloud accessible neutral atom computing plus hybrid optimization. So this is not necessarily just using quantum or just using classical, but using methods of both to find algorithms which go beyond finding just ground states. So that's my optimization. I would like to add one last thing on digital mode, just to get people excited, which is our next generation hardware, which is gate based, using high fidelity gates, as well as all-to-all connectivity with atom moving. And what this lets us do is have sort of the theorist stream of high fidelity, many qubits, and all-to-all connectivity in order to enable sort of many different interesting algorithms for digital mode optimization. So with that, I would like to conclude, and I guess we can go on to the Q&A.
Thank you very much, Jonathan. Lots of users have historically done Kubo-based optimization using annealers. So if they have a Kubo problem, should they just come to us with the Kubo formulation, or would you recommend something else?
That's a great question. I think this goes back to, I guess this maybe slight opinion slide back here on the challenge of encoding things into Kubo problems, which is that we're not, the Kubo formulation is not necessarily the most efficient way of encoding your problem, because typically when you do so, you lose a lot of information and structure about the original problem, which might be very useful for optimization. So actually, when coming to us with a problem, it is better to come to us with the original problem instead of necessarily coming to us with some Kubo structure. Because for example, if our complex network is very close to an independent set type network, then it doesn't necessarily make sense to come to us with a Kubo representation of that, but it can just tell us, hey, we want to find, the set of power stations that are maximally independent of each other. Oh, that sounds very close to an independent set problem, which then we might be able to find a hybrid algorithm which can more effectively solve that problem.
Wonderful. I wanted to, so in this webinar, we had a chance to answer 20-something questions. Feel free to submit more. We still have a couple of minutes, but a few points of order. First, on the website, on our website, under news and events, we have a whole list of events, both trade shows, conferences, and webinars that we are showing. We have a monthly office hour. The next one is actually tomorrow, where people can just drop in and ask whatever they want. We have an upcoming webinar, Quantum and Friends in Italy, where we showcase some of our Italian partners. We have another one, very interesting one at the beginning of November, about selling quantum computers to the board, not necessarily the computer itself, but selling quantum computing projects to the board, how to talk with the board of directors about quantum. And you also have recordings of past webinars, so you can see a lot of the work that we've done. For instance, there's a webinar that Deloitte had with us a few months ago showing their work in quantum reservoir computing using Aquila, and so on. The second point I wanted to make is that we've seen in this webinar the really wide range of problems that could be solved with Aquila. As Jonathan said, not every problem is a good fit for quantum computers in general, and not every problem is a good fit for Aquila. So we're very open to these exploratory conversations where you guys can come in and say, hey, here's the problem, or here are the problems that I'm interested in solving. Does this look like a good fit for a quantum computer? In return, we can show you some of the work that we've done in greater detail than we could in this webinar, and then see if there's a match. If there's a match, great. Maybe we find a way to work together. If there's no match, let's just be friends. Either way is fine. So I don't see additional questions. So how about I give everyone 2 minutes back? Thank you very much, Milan, Jonathan, and Fangli, for your excellent presentations, and look forward to being with you on the next event.